Okay, so apparently you weren't able to hear me for the last 2 minutes. Okay, I'm just setting up the Visual Studio Code session again. So we are going to need basically the same setting as before. 1 GPU, 2 gigabytes of memory is fine because we're later going to need some more memory, but we're going to do that in a Jupyter notebook. So currently we don't need it yet. And launch it. So while this is trying to launch itself, I might as well start talking. Okay, so you might already have heard it from Tapish. My name is Franz. I'm from the Casus Institute of the HCDR in Görlitz, nearby Dresden. And I'm going to talk a bit about the open standard for particle mesh data now. This session is in general going to be a bit less on the technical side, especially the practical sessions. Because on the one hand, Alpaca is really a framework for programming, while this is a software library and data standard with ecosystem around it. So I think it's more natural to have a bit more of an explorative approach on how you can interact with OpenPMD data and how you can write it. We are going to use the OpenPMD API. We are going to program some things in C++ as well as in the Python bindings. But yeah, let's look a bit back at what we saw so far in the last 2 days or 1.5 days of the workshop. Well, we have this situation, we have lots of possible backends. We don't want to write new code for all of them. Is there maybe a similar challenge in I/O? Maybe there is, because you might want to write files on the laptops that you have in front of your desk. You might want to write files to parallel file systems on HPC systems. Those parallel file systems have special things that you need to take care of, such as file striping or maybe subfiling. Now, some systems may have really lots of memory per host, some have rather scarce memory. Then the question is, okay, which file format do I use? HDF5 is widely spread. There's the ADIOS project, which strives for performance at full scale. Or do you maybe want to write ASCII data? Maybe there's something new around, or some workflow that just requires something that isn't really there yet. Going beyond file writing, what kind of data storage or data transport am I going to use? So will I even write to file? Maybe that's something that Michael already hinted at yesterday. Do I maybe want to stream to something else that is running at the same time? So for example, I have a simulation running concurrently with an analysis, and the simulation outputs data not onto the file system, but directly into the analysis. But how? Do I use shared memory for that, but that restricts me to exchanging data within one node? Or do I use some network? Wide area network sockets might work, but might not scale. So what specific networks are there on systems? Some have InfiniBand, some have Slingshot, some have maybe others. Do I want to compress data? Yeah, I mean, probably every one of us knows those friendly, regular emails about please clean up your files. So maybe you want to save some file space, some disk space. Maybe you also just see that you have a simulation that's running purely on GPU and has unused CPU resources. So maybe you want to compute the compression on the CPU. Maybe you also have a compressor that computes very well on the GPU. And which compression library are you going to use? What data path are you going to use? Yeah, some systems have specific hardware like burst buffers, which you can use to even out performance spikes, because in HPC, for example, it's very common to write data not as a constantly flowing thing, but there's one push where everyone writes and then it's silent again. So maybe there's a way to catch up those spikes, but maybe reality even shows that this doesn't always work for all kinds of applications. Do you write synchronously? Do you write asynchronously? Serial and parallel I/O, I already hinted at that with the serial and parallel file systems. And if you do parallel I/O, what aggregation strategy do you use? Do you use one aggregation strategy at all? How do you serialize data? So do you use a more structured format like the blue thing in the bottom that resembles the way that HDF5 writes data, or the bit more unstructured log format, log as in logbook, not as in logarithm, that ADOS uses? And maybe even beyond that, serialization is also where you need to start thinking about, do I write portable data files that I can take from one system that has 32-bit integers to another system that has 64-bit integers, or that has different byte orders? What are the read patterns? So there is definitely there are some questions that you need to ask yourself. And most of these questions don't have a clear answer, and most of those answers, again, are probably not easily implemented. So, for example, aggregation schemes. You have maybe something that just came up about performance measuring. You don't know before what is going to happen. So I'm going to start writing an aggregation scheme, and a month later you see it doesn't work. So I'm going to do it again. So there is some need for maybe not having all of this kind of stuff hard-coded into your application directly, but have some way to make it reusable. And performance portability doesn't immediately mean that you get free lunch, but at the same time, you just have a better starting point to say, okay, I have put this this kind of functionality needs to go into some external library or into multiple libraries, such as HDF5 or ADOS. And I need to be able to say, okay, I will use my simulation now on a new system, but maybe with new data that has different properties for compression. So I want to have a clear path towards how can I adapt to a new setup without writing everything anew. Looking at the other perspective, this was performance now. What is the typical workflow in a scientific facility? Theoretically, the easiest thing, let's say you have a Python application that works with NumPy, you need to store your data somehow. NumPy has inbuilt functionality to just dump the arrays onto disk, and you can read them again. Is this really portable in a workflow perspective where you might have not one single code, but you have one code that produces data, one code that analyzes data, one that reduces data, one that visualizes data? You might want to switch out codes that do the same thing and see how they compare. So also there is some need for standardization of data, and this kind of the bridge between performant I/O and scientifically standardized I/O is where we try to come in with OpenPMD. open standard for particle mesh data. One of the software projects, and not only software projects, but it's like I said, also a data standard that is used in our ecosystem, for example, in Picon GPU, next to Alpaca. So particle mesh data, what does that mean? It's the kind of data format that comes naturally to a particle in cell simulation, because there you have meshes, those are structured data, and within those meshes you find discrete objects, particles, which are unstructured listed data. So the mesh is simply an n-dimensional space that is divided into concrete cells, so it's discretized. For example, you have this room here and you say, okay, I split this room into single cells of 1 by 1 by 1 meter and measure the temperature everywhere. So you have a temperature mesh. For Picon GPU, there are, for example, electrical fields, but you can also think about, for example, pixels in an image. On the other hand, particles, like I said, discrete objects that have positions on that mesh. And for each position, or for each particle type, you need to list the position, and for numerical reasons also the offset of that position, but optionally can list more things that you want to describe or store. This is modeled in a standard, in the OpenPMD standard, in a hierarchical way. So an OpenPMD dataset is a series of iterations. An iteration is just, you can call it time step, snapshot, so there are different words for it in different contexts. But generally a scientific simulation or scientific code is going to produce data in somewhat iterative format, so that's what an iteration is. Those iterations can be stored in different ways. You can store them in such a way that each iteration is its own file. You can store one file in total and just have single groups for each iteration within that file. Or there are more customized layouts optimized for specific backends such as ADOS2. And each iteration is then a dataset of meshes and particles. And at the end, you have the actual n-dimensional heavyweight datasets where your terabytes of data are going to go. For example, an HDF5 that can look like this. This is a dataset produced by Picon GPU. So you have the B field, an E field that is composed of X, Y, and Z. This is maybe something where I need to pay attention to, because Picon GPU is fundamentally a three-dimensional code. So each field is three-dimensional itself. So it has, like, if I modeled this room, we would say 20 by 20 by 50 meters. I'm bad at estimating, but that's a three-dimensional thing. But still, if you say I have a three-dimensional mesh, you have to decide if it's scalar or a vector field. Like the E field is a vector field in that sense that each single cell is a direction, is a vector arrow. While, for example, if I wanted to model this room as a temperature doesn't have a direction, so you skip this last X, Y, Z bit and say, okay, it's a scalar value. In case of this example, we have the charge and energy densities. And then down here we see particles E and I for electrons and ions. And we see that ions are defined by what I mentioned before, position and position offset, but also by more domain-specific things defined by Picon GPU, such as weighting, momentum, mass, and charge. This is an example dataset in ADOS2. So basically the same structure, but in a different format. And like I already said, we have also a JSON and very recently a TOML backend. with this slide, I'm cheating a bit right now because this is a shortcut format for JSON that is actually still a pull request. So if I use the actual output produced today by OpenPMD, this would be 2 times longer because the data types would be annotated. But we decided at some point to make this optional for legibility purposes, and someone asked me to make the slide more legible, so I decided to cheat and just take something that's still under development. And our recent release that was released like 2 weeks ago added also a TOML backend, which is really simply implemented by converting the JSON values to TOML at the end when writing. And this is maybe also coming back to when we have to the question of, okay, we have a workflow where we want to use OpenPMD, but the old backends don't really fit. This was added for supporting experiments workflows, where if you compare simulations with experiments, a simulation is somewhat omniscient within the thing that it simulates, so it knows all the metadata. In an experiment, we need some workflow to input the metadata, and the idea was to have a configuration file that is OpenPMD formatted. And TOML is a very good format to support configuration files. So by just adding this kind of conversion functionality and simplifying the markup, that's why we did that, or why we are doing that. We have this functionality added, and this kind of workflow integrated into the wider OpenPMD ecosystem. So maybe that's an example for what I mentioned earlier. Otherwise, JSON is just neat because it's easy. Everyone kind of knows it. Yeah.
Why not YAML instead of TOML? Is there a specific reason?
The very specific reason is because we already had TOML for some other functionality in OpenPMD, and so it was the more straightforward thing to implement because most of the helper functionality was already there. So no specific reason as to this data format is better than that. I think TOML is a good fit for configuration kind of things because it is a kind of extended configuration file format from the simpler.
It's just if there is a deep hierarchy, then it's difficult to. It's more difficult to follow. But maybe it's just.
I think that this is actually one of the specific reasons why we added TOML over JSON, because JSON is difficult to follow when we already are there when the hierarchy gets deep. Because in TOML I could, for example, just write. I don't have an example right here now, but when I have a deep hierarchy in TOML, I can write something like data.100.attributes and then list all those attributes that are at level 3 or 4 here, like cell depth, is 10. And basically that allows me to write things without having to count indentation. So my personal opinion is that it's very well fit for actually writing deep hierarchies.
Okay, so that's.
There's a question in the chat. Could you, on the right hand, open the chat?
Probably also depends on the sparsity of your tree. If you have very deep but very sparse tree, then this is very convenient. If your tree has all the leaves that it could possibly have from all the levels, then this is probably very convenient.
I must be honest here, this is the first time in my life that I hear about the word nodal. Can you maybe unmute yourself or explain what exactly you mean by that? because I'm currently not sure if I understand the question correctly.
Can you hear me?
Yeah.
Okay. Well, by nodal, I mean the corner points of finite element meshes. I just saw your particles within the cells floating around, basically. I just wanted to know if there's something like a mesh connectivity and the corner points of the element. And that's the basic question. Just to make sure that OpenPMD is not covered just to this particular use case of having particles that we're using in this workshop.
Also, what exactly distinguishes a finite element mesh from what I showed so far?
Well, just general unstructured finite element meshes in terms of you need connectivity. So you need basically the corner points of the cell and then describe connectivities. This kind of extra data to describe the mesh, basically.
Okay.
Because we have seen only the 2D heat equations, so it's like a structured grid, easy to describe. I just wanted to make sure what the scope of OpenPMD is, whether it's only for particle simulation and some kind of background mesh, or whether it's for general meshes as well.
Let's say, so there are different geometries defined. The default one is the Cartesian that we are going to use in this workshop. Beyond that, OpenPMD, so I would actually I need to be honest here, I would need to see an exact example and then would need some time to see if we can model this into what already exists, or if we, for example, would need to define a standard extension, because that's the normal way, which I'm also going to cover in some more some further slides. The basic standard defines roughly what we have seen so far. And for example, for Pick on GPU already, we needed some domain-specific information, which we did not put into the standard because it just isn't generic a particle mesh standard relevant. So generally, OpenPMD tries to be extensible towards use cases that aren't considered so far. I cannot answer at this point how I would model your use case.
Okay, thanks for now. Maybe I'll do some research and find a good example and then come back. But thank you.
Yeah, I would also be interested in that. So do feel free to reach out.
Okay, thanks.
Yeah, so those are OpenPMD datasets in 3 backends for now. Roughly, so we are going to start over to the first interactive session. The idea or the plan that I was having was to do some basic data modeling today to continue with the heat equation. So I'm not even sure, did we show the JPEGs created by the heat equation? I think not. Did we? Okay, cool. So instead of the JPEGs, we are going to write output to OpenPMD. And are then going to look into how we can configure backends and use configuration files to switch, for example, between HDF5 and ADIOS, how to enable compression. And then we are going to switch over to a Jupyter Notebook for visualization purposes. And the final goal for today is to have a setup that visualizes a heat equation simulation while it's running. So to switch from file I/O, which we will do at first, over to streaming I/O. Tomorrow, I'm planning to go a bit more into the ecosystem by showing first the OpenPMD viewer, and after that, ParaView to visualize a real-life dataset produced by Pick on GPU, and then come back to some more detailed modeling for OpenPMD data. So about particles, constant components, particle patches. And then for the final session, I'm planning to go over to parallel I/O, what you need to pay attention to, how parallel I/O works, what you need to take care of, what you don't need to take care of. And there's additionally one advanced session, which is just on a, let's say, very detailed but still common case that comes up in many real world software where you can elide data copies in the case that data needs to be prepared before output. So this advanced session might also come at the end of the day. This is the first time I'm doing something like this, so I'm not really sure how the timing will work out. So yeah, this is a bit of my wild card. For the ParaView session, I'm mostly planning that one to be non-interactive, but you can follow along. If you want to follow along, then you would need to download ParaView before tomorrow, and especially you would also need to download the data that we are going to visualize. The data is on Lumi. It's around 6 gigabyte. So if you have a German internet connection, maybe download overnight. Otherwise, I also have the data set on a USB drive here for those in the audience. Now I have 3 USB drives at home. One of them is too small, the other one is normal but always gone, and this one thinks it's a CD. So I don't know what exactly is going wrong with this thing, but if you plug it in, it will appear as a CD and a USB drive, and especially if you plug it into a Windows computer, it will actually try launching software. So proceed at your own risk. The dataset is on there. I would just... You can also download it from Lumi. Yeah, all right, to head over to the first session, we are going to work with the OpenPMD API, which is the reference implementation for OpenPMD, and the thing that I'm mostly working on within the OpenPMD ecosystem. It's written in C++, currently C++ 17, and has bindings for Python. We're going to see both of them. Documentation is online. And yeah, there are packages for some of the more common package managers. Someone post the link. I will post or maybe someone can post the link in the Slack or the chat for the download of the dataset. Or maybe I'm just going to do it in the break. Okay, so let's switch over to the first session.